All right, so let's look at this question. We have two member frame A, B, C showing here, and have a two loading 8 kilonewton and a distributed node on member BC. So we have to determine the horizontal and the vertical component of reaction force at point A, reaction force point C, and the point B. So first of all, we have to disassemble these two member frame into separate members. So we have member AB shown here, member BC shown here. So we have AB, BC. Okay, so the reaction force at point the reaction point A will be shown here. So here is AX. Here is let's put it AY. So at point B, so BY, BX. On the member BC also is BX, is BY. C, we have CX, CY. Okay, so look at these two forces, BX, BY, and point B on member AB, and BX, BY, and point B on member BC. So these two forces have same value, but their direction are different. That's it. So now we need to put on the external force on the number AB. External force showing here, 8 kilonewton. And we have a distributed node on member BC. So normally we just convert this distributed into equivalent point of force. So the equivalent point of force, because this is a distributed node, so the point of force is at the midpoint of the beam BC. So the value of this equivalent force would be 3 kilonewton per meter times the length of this beam BC equal to 6 kilonewton. Okay, so 6 kilonewton, and this equivalent point force is at the midpoint. So we move here. So this is 6 kilonewton at midpoint. The mid distance will be 1 meter. So look at these two free body diagram. One AB, one is BC. We found for each of them we can write down 3 equations of equilibrium, but there are 4 unknown forces. So that means we cannot solve it just by these 2 forces, just by the 3 equations of equilibrium. So that means we have to borrow the force value from each other members. So let's look at how to do it. So I would like to first look at member BC. So at member BC, if we write down the equation of equilibrium for bending moments at point B, AB, and we assume the positive direction is go clockwise. So so BX, BY have no bending moment at point B. 6 kilonewton, the point load have a bending moment at point B. So it's 6 kilonewton times the lever arm 1 meter, because it's go clockwise, so it's positive. And the CY have a bending moment as well, and it's go counterclockwise, so it's negative. So times the lever arm 2 meter equal to 0, because CX have no bending moment on point B. So then we can calculate CY equal to 3 kilonewton. So CY equal to 3 kilonewton. After we know the CY equal to 3 kilonewton, then we can write down equation of equilibrium in vertical direction. We assume the positive direction go upward. So then we check, we have 3 force in vertical direction. Then it's BY go downwards, so it's negative. BY and the 6 kilonewton go downwards, so it's negative sign as well, 6 kilonewton, and the Cy go upward. So then we have positive Cy 3 kilonewton equal to 0. So then we can calculate the By equal to negative 3 kilonewton. Okay, so By is negative 3 kilonewton. So here is By, negative 3 kilonewton. That's mean because these two By at the point B on number BC and By at the point B on number AB have same value. So here is By is equal to negative 3 kilonewton. That is what I mean. So we have to borrow some value from other numbers. So here it is. So we have By showing here on number AB. So once we know the By, so we can move on to calculate the force on number AB. So we know we have to Bx, Cx, but we leave it later. Okay, so first of all, look at the number AB. So if we write down the equation of equilibrium of bending moment equation of equilibrium, so we at the point A we have equal to 0. So assume the positive direction is go clockwise. So we have 3 force have bending moments on point A. One is 8 kilonewton external force, one is By, and one is Bx. So if we draw the dimension, so we know here, so 2 meters is showing here. It's 2 meters. Here is 1.5 meter. And the distance from 8 kilonewton to the point of 8 kilonewton to point A is 2 meters. Okay. So now we write down the bending moment equation of equilibrium. So we have 8 kilonewton. 8 kilonewton has a lever arm 2 meters and go clockwise, so it's positive. And then we see By is go counterclockwise, so it's negative, and By is 3 kilonewton times the 2 meters. This is the lever arm of By. And let's look at the Bx is also go counterclockwise, so it's negative. Bx times the lever arm is 1.5 meter, okay, equal to 0. So from this equation, we can calculate Bx equal to 14.7 kilonewton. Okay, this is Bx. So after we know the Bx, then so the Bx is equal to 14.7 kilonewton, and we know Bx is showing here. So once we know the Bx, if we write down the equation of equilibrium, let's look back at BC. So number BC, we have, so if we just, okay, so if we look at the number BC, if we write down the equation of equilibrium in x direction, so if we say the positive direction is go to right hand side, so we have Bx minus Cx go to left hand side, so equal to 0. So Cx equal to Bx equal to 14.7 kilonewton. Okay, so we know Cx, we know Cy, we know Bx, we know By, we know these two here. So the only two unknown is ax and ay. Okay, so to calculate ax and ay, we have to using the other two equation of equilibrium. One is Fy in vertical direction, equation of equilibrium. The other one is in x direction. Okay, so before we go for these two equations of equilibrium, so let's calculate the components of the 8 kilonewton, because 8 kilonewton is not on the x direction or on y direction. It's go to, there's an angle. So the angle value is showing here. So this is an angle. So we have to calculate the components of 8 kilonewton. So if we calculate that, so let's look at here. So 8 kilonewton have two components. Let's draw the 8 kilonewton over here. So this 8 kilonewton and have two components. This 8 kilonewton. And if we see, this is the angle theta. Okay, so look at this geometry relationship. So we have we can easily know the sine theta is equal to, look at here, so 3, 4, 5, so equal to 4 over 5 equal to 0.8. Cosine theta is equal to 3.3 over 5 equal to 0.6. And we know this component, so the component in vertical component is 8 kilonewton, vertical component. So 8 kilonewton times the sine theta equal to 8 times 0.8 is equal to 6.4 kilonewton, and the horizontal component is 8 kilonewton times cosine theta equal to 8 times 0.6 equal to 4.8 kilonewton. Okay, so this is two component of 8 kilonewton. So 4.8 kilonewton, 6.4 kilonewton. Okay, we have these two forces. Then we can write down the equation of equilibrium for the number AB. So for number AB, let's just replace this 8 kilonewton with two components. So we just replace this. Sorry. So we have two force. These two force, this is 6.4 kilonewton. This force is 4.8 kilonewton. Okay. So now for the in y direction, in vertical direction, we have so we have AY. First of all, we have AY. So going downwards, so it's negative, and we have 6.4 kilonewton going downwards is negative as well. And we have by go upwards, so it's positive, but the value is negative 3 kilonewton. Okay, this is the vertical direction, the equation of equilibrium. So based on this, we can calculate the AY is equal to 9.4 kilonewton. Okay, negative, don't forget negative. Okay, so this is AY, and if we write down the equation of equilibrium in x direction, we assume the positive direction go to the right direction. With AX is positive, and plus 4.8 kilonewton is positive is over here, is positive as well. And bx go to left hand side, so it's negative, minus 14.7 kilonewton equal to 0. So from this we can calculate the AX equal to 9.9 kilonewton. Okay, so we got AX, AY. This is two component of the reaction force at point A. We have CX, CY. This is two component force at point C. We have BY. We have BY. We have BX. So this is two components at force at point B. So now we solve all the components.